So essentially what happens here is initially it is something like this. And it has been extended, so let's say it got compressed. So this change in x is it basically is just a change in x. So which also means that this x and this x should be the same. Right, they should be the same distance because area is the same. So the volume double, x double, essentially that. So what you need to find is this value. So why do we need this value? Because this is the same type of question as we talk about in tutorial. We can actually reuse this diagram here. So this is in state 1. So in state 2, what happened here is that once it has been expanded, you still have F ATM, you still have work piston. Here, this is still F from the H2O, but now this is F2. So the initial one was F1 because from the new pressure. So then you will get an additional new term here, which is F of the spring. Right, because now the water has expanded, so it will be pushing against the spring, so which means the spring will push back. So then, which means your equation here should look something like this. So F ATM plus F spring plus weight of the piston equals to F2. So, and then we know from the previous diagram, which is diagram 1, that this is just F1 plus F spring equals to F2, which also means that P2 is just P1 plus F spring over area of the piston. Which in this case, let's put it over here, P2 is just P1 plus Kx over A. Because that's how much work the spring is doing, which is X. So in order to find X, you actually don't really need to do anything. So X is just V1 over A. So you don't actually need to care about V2 because, like we said here, the X is just the same. Basically the increase in X is just the initial X, the initial distance. So this is X. So after it has doubled, so from X it becomes 2X, basically that. So all you need to find is X. X is just volume over area. So you sub this in, P2 should be approximately, won't be exact, it's actually 199.9, but it will be approximately 200 kilopascal. Exactly have to draw me the free body diagram. You can just start straight with this equation if you know what is happening, because I mean I'm not teaching dynamics here, so it's fine. You can start straight with this. You don't really have to show me everything here. Okay, but of course, if you find it hard to do to understand, you draw this out. No issue there lah. Just that you don't really have to do that for me. Okay, so is everyone fine with part B? Okay, then we can move on. Can we? 1, 2, 3. No objection. Let's move on. Okay, let's look at C. So C, sketch the PV diagram and calculate the boundary work during this process. So just a continuation of this question. So you need to sketch the PV diagram. So here, PV diagram. We are dealing with water, so don't forget the saturation line. Okay, so step 1, we know that this is a at step 1, the water is at saturated vapor. So you know that this is where you start. So this should be your point 1. And this should be your V1 also lah. And then, so step 2, we know, you kind of don't know also, but do you know or you don't? Yeah. You can also check the table if you want to, but in general, it does make sense one lah. So we know that volume has increases, pressure has increased. So cause pressure change from, okay, if you actually went through the trouble of looking for the answer just now, this should be this value. I didn't write out cause it's just from the table lah. So the initial pressure is 120.9. The new one is 200 kilopascal. Then volume also has doubled. So based on this, you know that it definitely has to be a saturated, a superheated vapor, right? Then it definitely should be somewhere here. So how does it change? How does it move over there? This is a piston cylinder device with a spring. So if you have a linear spring, then this movement is just a linear movement. Okay, so it kind of just look at this. You don't really need the label with the value because here we just ask you to sketch the PV diagram, that's all. Of course, it would be better if you can put in all the value. So it basically looks something like this. So again, if the question doesn't have a linear spring to it, then it is just a curve. The point will be at the same place, but it's just a curve. So you need to calculate the boundary work. So the boundary work is just the area under the graph for a PV diagram, the closed system here. So it is just PdV, which is what is this value that I use here? Let me see. Okay, so here now, at one glance, let's say if you are just looking at this diagram, it will seem like you actually need to do a bit more work also by simply instead of just calculating all these things. But actually you don't really need any extra information here as well. So this is the area under the graph. So area under the graph is simply just a trapezium, right? Which means this is half this distance plus this distance. So it's 120.9 just that I wrote just now, plus 200 and this distance. So the difference in the volume is actually just V1, capital V1. Because again, the volume has doubled, so if you minus back, you get back the same value. Or if you want a more accurate representation, it's just small v1 and mass lah, since I wrote mass here and the small v here. But otherwise, they are the same thing. Okay, so it's just a capital V1. So maybe I put it in variable so that it's clearer. This is P1, this is P2. And yeah, then final answer is just this. Alright, then let's finish this up. So we go to part D, the last part. If the water loses 5 kJ of heat during the process, determine how long the resistor heater is turned on. So again, let's draw this thing. Okay, then we see what are the forces that we have. So obviously we have a boundary work out, right? So because boundary work out, then which is from here. Then we have work in from electricity because we have a resistor heater. Again, remember we talk about the energy in terms of the energy that cross the boundary. So even though it's a resistance heater, it's still work electric work. It's not heat in. And based on the question, there is a heat out. Q out of 5 kJ. So this question, you need to determine how long the resistor heater is turned on. So obviously here, you need to start with the energy analysis, which is Q minus W equals to delta U. Of course, if you want, you can also write this lah, but this one not necessary. This one I can just cancel off. Okay, so Q minus W equals to Q minus W equals to delta U. Then we sub in all the value here. So, or rather, maybe not value. We sub in what are in this case, what are there in this case, or we expand this. So, in terms of Q, then we get negative Q out, right? We have a Q out here. For work, we have both work in and work out. So work out here is boundary work. Work in is electricity work, equals to U2 minus U1. So this question, since Q is given into a kilojoule, you can solve it in kilojoule or you can divide the whole thing by mass as well, that one doesn't matter. Okay, so then we rearrange this, you get WE minus WB minus Q out equals to M small U2 minus U1. Okay, so as usual, this kind of question, you do have two ways of solving this. You can move this over here to change this into H, or you can just solve it as it is. Okay, so in this case, there's no real reason for you to move the boundary work over because you have calculated the boundary work in the previous section. So you can use that value directly. But if you decide to do that, like you move the boundary work over the other side and change the whole thing into MH2 minus H1, you are not wrong as well. Actually, you will get similar answer. You can also try that out on your own free time if you want to prove the case. But in this case, we are not doing that because waste of time. I mean, not really waste of time lah. Same thing lah. We have calculated the boundary work, so it doesn't really matter. So we know that electricity work would be VIT, because this is in terms of joule. And so boundary work is just 1.1381. Q out is 5. Now one thing that is very important here, this one needs to divide by 1000 because if you just do VIT, what you get is joule. So you need to divide that by 1000. So then here this is 0.005, then you have U2, U1. So you need to find U2 and U1. So for U1, we go back to T1 equals to 105 degrees Celsius, U1 equals, saturated vapor. U1 is just UG at 105 degrees Celsius. U2, a bit more troublesome. We know P2 is 200 kilopascal. But what other information do we have about 2? What else do we know about state 2? because we always need two information, right? So from previous calculation, we know that P2 is 200. But what else do we know? If it is just superheated vapor, you don't have enough information also, right? Because superheated table doesn't really help you. Saturated, then yes. Because saturated vapor and liquid you can get from the table. But if it's a mixture also, it doesn't help you. Just like superheated vapor. You know it's from that table, but that is not one information that you can use. Actually, I think this answer a bit wrong. But in the meantime, you think first, let me check. Let me check the answer a bit. Stage 2. What other information do you have here? So the other thing that you know about state 2 is that here, you know that volume has doubled. So you know volume 2. So with this one, right? You know V2. But of course, V2 is not an information that you can use. So you need to convert it to the specific volume 2. You need the small V2. So meaning here, you need V2 over mass. Okay, so V2 will be 0.0079 something. So it will be V1, which is this value. It will be the capital V1 multiplied by 2, then divide by the mass, which is 0.005 gram. And here, you should get this value. So based on this value, then only you can go to the superheated vapor table to get your U2 from interpolation. So this one you will need to do. You will need to interpolate. And so if you solve these, then you will get the answer that I uploaded will be a bit wrong. It's a bit wrong because I forgot about the mass. I will, when I remember, I will correct it. But as of now, this is the answer. After I check, I calculated on the spot. It might be a bit wrong. Let me know if it is wrong. Because sometimes, right, some of the answers here are not exactly correct, and then during exam, no one got it correctly, so I didn't notice the answer is wrong. So yeah, there was also cases like that sometimes. But I do double check. I don't rely solely on my answer. If I think what you did is correct, but then somehow it's different from my answer, I will check again on that. But then yeah, if everything is wrong, then I don't check out sometimes. Okay, now there was also a case where in one of the past year, I think last year or the previous year, I have similar question, but not exactly in this way. That time, I asked them to look for voltage, I think, but I forgot the time. So I didn't give time, so there are two variables there. So in the exam, no time to give you. So in those cases, right, what you can do is just find them in terms of per time. Yeah, so actually this paper also got one issue later that I can show you. But these are not serious problems, like as in you can really still solve them. But probably just like I say, if like in this case there's no time, like if the time, let's say if voltage is not given, then you just look for it in terms of like per voltage. That's all. But Yeah, like voltage not likely, but the time I forgot about time because I accidentally just used IV is P equals to IV instead of W equals to IVT. If you ask me the exam if I found out that that's the case, I will also tell you to do the same thing. Just assume that it's in terms of time, then just fine. Or you just say that assume it's 1 second, then you continue with the question, something like that. Don't waste too much time on this kind of thing lah. I mean, but if you get stressed out, it's like I know enough information, how just ask me. I won't teach you how to do, but then if there's issue with the question, of course I will let you know lah. Okay. We try not to have this kind of problem, but sometimes it's unavoidable. Okay, so is there any question? Try them out on your own and see if you can get the same answer. So again, if the answer is different, maybe you discuss with your friend first. Still cannot, then message me. Then I will see if it is my issue. Okay, then I will move on. So question 3, I actually won't discuss, but we will just read it. Okay, define the perpetual motion machine, so ppm of the first kind, ppm1, and the second kind, ppm2, and provide one example for each of them respectively. So obviously they don't exist, so your example is a bit more imaginary. So you just explain to me. Okay, maybe we just talk about it like verbally like this lah. Now, PMM, perpetual motion machine, is actually very easy to remember that definition. Why? PMM1 means the device that violates first law. PMM2, device that violates second law. But of course, second law, we know we have two statements, so there are two things there. So let's say PMM1 is a device that violates the first law. So what is the first law? First law is conservation of energy. So meaning if it violates first law, it means that it is creating energy, basically that. Or it's destroying energy, but I don't think you will have a good example on destroying energy lah. So the example here will be, you just said, is a steam power plant that can work indefinitely without requiring any external energy input. This example is actually in the lecture notes, so you can look at the one that I draw kind of there. So then you explain how this is not possible, basically that. So explain how the law of thermodynamics limits the feasibility of these perpetual motion machines and how they violate the principle of the thermodynamics law. So you give me the definition, like I said, PM1 and PM2, give one example and then explain why that example cannot happen due to the first law or second law, basically that. Okay, so second law one, the one that violates, you can also say something like, remember, we say that if the device is supposed to work in a cycle, a heat engine, it cannot work in a cycle without rejecting heat through an external source. It cannot just keep taking heat and then generating work, getting heat and generating work. You need to reject some heat. So that is actually one example. So things to note, when you are dealing with my type of exam question, you will also notice when you are doing the past year, you cannot run from theory, so don't ask me whether theory is coming out. I will always ask them, okay? But my theory mainly are more on understanding rather than like forcing you to memorize the definition. Like if I'm asking you definition, they are probably definition that you should know by now. Something things like if I ask you what is the first law, you should know that it is conservation of energy. You don't really need to give me like word by word the explanation. If you just tell me first law is about the first conservation energy, what is conservation energy? Energy cannot be created or destroyed, it can only be converted. That's all. You don't really need me to give me like word by word. Just tell me what you understand. That's good enough. Okay, so we jump straight to B. So B is the question where I give one less information, I think. Okay, so question 3B. An ideal Otto cycle has a compression ratio of 10 and produces a net power of 100 kilowatts. So I'm just giving you about Otto cycle. Actually, this one is a very straightforward question. So the state of the air input at the beginning of the compression process is 90 kilopascal and 57 degrees Celsius. Air can be assumed to be an ideal gas with constant specific heat capacity. So you are asked to use constant specific heat method. So you use the equation, don't use the table. So when I say this is at 300 Kelvin, so just stick to the value at table A2. Meaning, in this case, K is 1.4, R is 0.287, Cp is 1.005, Cv is, what is Cv? 0.7 something. But it should be in the table lah. The exact the table is given in your exam, so you can refer here. Maybe switch. So when I say 300 Kelvin, this is the table that you are referring to. So this is given in the exam also, so you don't need to memorize all those values, just refer to this one. But again, by now you should be kind of familiar with the values here lah. At least the 1.4, 0.287, for me I never remember CV, but because I rarely use it. But you can also calculate just from the others, so not big deal here. Okay, so we are back here. Okay, so we are just dealing with an Otto cycle. So you need to sketch the PV diagram so you can see the question very clearly. I ask you to give me the flow direction, heat and work transfer, so you have to include all the heat and work transfer of the cycle as well, not just the shape, to get the full marks. So PV diagram. So PV diagram for an Otto cycle is just 1, 2, 3, 4. Okay, so these are the direction is labeled. We know that this is the BDC, this is the TDC. You want to say V1, V2 also okay lah. Doesn't really matter there. Then, of course, now in your notes, you will see that it mainly only label Q in and Q out. But of course, here I ask you to include work transfer as well. And you should be aware that, so 1 to 2 is compression, so it is work in. So 3 to 4 is expansion, so this is work out. So you should be aware of this as well, even though in the notes, we didn't really label these two. Okay, so then we move on to the question itself. So 2, just basic question. Determine the thermal efficiency of the cycle and subsequently the rate of heat addition to the system. So you need to find out what is the thermal efficiency and also the Q in. Then after that, 3, determine the maximum temperature and pressure of the cycle, which is T3 and P3. So now this question, you might think that it goes a bit of the other way around, because usually when I teach you this, you find out the temperature first, then only you find Q in, then you find thermal efficiency, right? So now, let's say if you do that, it's fine. I will just mark accordingly. But so why is it that I can go the other way around with this question? Hey, wait, actually you actually cannot find, I think, if you don't if you go from the based on the usual flow. But again, this one, let's see if it is given in the question here. So these are the equation here now. So you can see that we actually have this Otto cycle equation for constant specific heat. So this equation, reminder, you cannot use if we are talking about variable specific heat. Okay, you can only use them when they are when we are dealing with constant specific heat question. So which is the case here. So which means the first one asks you to find the thermal efficiency. You can actually just use this equation, which is the Otto cycle equation. So you sum in R, in this case R is 10, K is 1.4, so you should get the thermal efficiency answer, which is this. So and then question asks for the rate of heat addition. So meaning you need to find capital Q in dot. So we also know that thermal efficiency is equals to work net over Q in. And this question actually gives you net power produced as well, which is 100. So you divide by this, you will get heat transfer, the rate of heat transfer. So easy marks here. But of course, just like you guys, I forgot about assumption also. So then maybe we just write at 3 lah. Okay, so assumptions here. So what kind of assumption does Otto cycle have? So don't forget, if you are dealing with a gas cycle, meaning something that you are dealing with, when you're dealing with gas or ideal gas, you should always assume air standard assumptions. Okay, this you cannot use for water, but when you are dealing with air or gases, then you should always assume this. Then as usual, KE and PE are negligible. So again, this kind of question, they are quite continuous. So remember I mentioned don't pay too much attention to the marks allocated to the question, because like in this case you will see that number 2, why is it that you only have 2 steps but actually there are 6 marks there. The assumption marks I put at 2 also lah. But let's say if you write in 3, I will still give you back the marks. Okay, so that will be okay, fine, because sometimes I find something else first, so I put a mark over there. But you might not have the exact same steps as me. But for me, overall is still correct, then that's fine. Alright, then we go to the last part. So we need to find the maximum temperature, which is T3, as well as pressure, also P3. So you need to find T3 and P3, which also means that we go back to the standard way of solving this. So first off, we need to find what is T2 first. We know that I close the question. Wait up. Okay, so we know that T1 is 57 degrees Celsius. T1 is 90 kilopascal. Okay, so we can start solving from here. So from T1 to T2, then so T2 over T1, so we know that this is, so for constant specific heat question, always remember that we use the isentropic relation equation, which is P2 over P1 here. Which are these equations? Are they given here? Yeah, so these equations. Again, so all these equations, they are all for constant specific heat. We don't use them if it is variable specific heat question. Variable specific question, just use the equation, just use the table and ideal gas law or equation of state, those things. So all the equations here are given for constant specific heat. So we have this relation here, so you can see that based on the pressure ratio, or rather, sorry, pressure ratio is actually another question. It's another type, you don't use it here. We use the volume compression ratio. So this one is actually volume, I wrote wrongly. So V1 over V2, which also means that this is just R, K minus 1. So from here, you can get the T2 value. Of course, don't forget that you need, these are all absolute temperature, absolute value, so your temperature should also be converted. So this is 330 Kelvin before you can use it in the equation. So you found T2 now. So once you found T2, then now you need to move on to T3. So this question, so now you can see that actually the reason why this question are split into so many parts is actually to guide you. So let's say if I ask right from the start to find this T3 and P3, it might not be as the solution might not be as obvious as it is, because here I actually ask you to find Q in first. So you found Q in, right, which means that you also know that Q in is m dot T3, sorry, H3 minus H2, which in the, sorry, this M, this is Q. Or the dot should, wait, yeah, the dot is here, sorry. Now, so which means, so this is CV, T3 minus T2. And this is where error from my side comes from. I forgot to give you math drawing. So yeah, so this is the case where but the thing is, you see, you know how to solve this. You just don't have that value. You can just assume mass equals to 1 kilogram per second. If you don't assume also that you solve it in terms of kilogram per second, what to do? This one is fine. This way is fine. It's my mistake. So, but you can continue to solve it without that value. Okay. So yeah, then if you continue, let's say if you just assume this is 1 kilogram, then this will become Q in instead. Then CV T3 minus T2. Then you reuse the value you calculated just now. So CP is 0.718. Then T3 minus T2. So T2 from the previous question, what's the value? Okay, should be this value. Okay, then you will get T3 equals to 1060 Kelvin. As for pressure, so don't forget that we are still looking for pressure, not just temperature. So as for pressure, then we start from state 1 again. Now for pressure, actually you can just keep using equation of state, so or the ideal gas equation. So you can see we know PV equals to PV, right? So P2 is just P1 T2 over T1, then this one is 1, sorry. So V1 over V2, then R. Then after that, once you found P2, then repeat, do the same thing. So this time these two can cancel off. Then you get P3 equals to P2, T3 over T2. So this should give you the answer as well. Then, yep, that's all.
H 是什么？H 是什么？
Okay, so is everyone done with this? Then we move on to the last question. Okay, so last question is it's a recurring question. As in question 4 is always about refrigeration system. At least so far lah. For you guys it will be the same also. But of course I do change this question around a bit. Now, some of the students complain to me they don't have enough information, but I don't think that's the case. But anyway, let's discuss. I do have the answer here. Okay, let's look at the question and see whether you think you don't have enough information for this. Okay, so a refrigeration system is designed to ensure, so it always comes with some story. So it's designed to ensure the freshness of perishable food item at supermarket with an ambient temperature of 27 degrees Celsius. So the first thing that you know is that the ambient temperature is 27 degrees Celsius. Is this useful for the vapor compression cycle? Probably not for now. So the refrigeration unit, which operates on a standard refrigeration cycle. So when I use the word standard, it kind of don't mean anything. It means that we haven't modified it, that's all. Doesn't mean that it is ideal. It is required to keep the refrigerated space below 4 degrees Celsius. So the refrigerator space needs to be below 4 degrees Celsius, meaning 4 degrees Celsius is the maximum temperature, by removing 900 watt of heat. The coolant enters the expansion valve as a saturated liquid and leaves the, so R134A, take note, enters expansion valve as saturated liquid and leaves the evaporator at 100 kilopascal and negative 10 degrees Celsius at a rate of 0.00642 kilogram per second. Okay, so what we know here is this. This system removes 900 kilowatt of heat. And then it is saturated liquid here. It leaves the evaporator at 100 kilopascal and negative 10 degrees Celsius. So this is 100 kilopascal, negative 10 degrees Celsius. Mass flow rate is 0.00642 kilogram per second. So you will notice that I never make use of the 27 degrees Celsius and 4 degrees Celsius because that two temperature, what are those temperature? Can anyone figure out? What are they? The 4 degrees Celsius and 27 degrees Celsius. They are the TL and TH. So this is your refrigeration cycle. It is trying to keep this space at negative 4 degrees Celsius or below lah. But of course, or below then you cannot calculate. So we keep it at 4 degrees Celsius. So ambient temperature is 27 degrees Celsius. So this is your work in. So this is actually your QL. Then QH. Makes sense, right? Because this is the ambient. This is the refrigerated space. But of course, if we zoom in and we only look at the refrigeration cycle, then these two temperatures are not useful at this point. Right? Okay, so we look at the question now. So A, sketch the TS diagram, blah blah blah. So this one, I think I won't show the TS diagram lah. Okay, maybe we show. Like I say, I always draw first before I solve. So maybe new page. So question 4. So we draw a TS diagram. At this point, so let's see, do we have enough information to determine whether this is an actual, okay, if you read until C, then you will see that this is an actual cycle because there is an isentropic efficiency given to you. So, but then otherwise you probably wouldn't notice that, but of course you should at least draw an ideal one, but now let's see. So if you draw a actual one, based on the information that is given to you, sorry, let me jump around a bit first. Don't forget assumption, this one I'll just leave it here for you to write. We are given, and then from the question, we are given that P1 is 100 kilopascal, T1 is negative 10 degrees Celsius. Let me write out all the information first. And then mass flow rate is 0. So mass flow is 0.00642 kilogram per second. And we know that state 3 is saturated liquid. Okay, so that's pretty much all we need here for now. Okay, so you have P1 and T1. As I mentioned, usually if you are given both temperature and pressure, it will mean that it's either superheated vapor or compressed liquid. But of course, it would do well for you to try to check it also. So meaning your 1 should start somewhere here. Okay, let's zoom in a bit. So your 1 should start somewhere here, because if you check P1 and T1, it is a superheated vapor. So, and since this is an actual cycle, you just draw something out here. Then, so this will be a 0.1, this is a 2s, this is your 2. Three is a saturated vapor, just now we saw in the question. And 4, as usual, should just be somewhere here. So you have your work in here, then you have QL here or Q in, and you have QH here or Q out. So these are all required. The only thing that I require from you. Maybe the 2S line maybe draw a bit more clear. Okay, so the TS diagram should look something like this, an actual one. But again, based on the information that are given to you. Okay, let me go capture the question first. Okay, so now at one glance, this question does look like it is lacking a lot of information, because it seems like you only know about 1 and maybe P4, because we know P4 and P1 is the same. And here we know that this is 100 kilopascal, but we don't really know what is the higher upper pressure order. Okay, so at one glance, it does look like it doesn't have enough information, which is also why, again, I speed up the question. So like I said, usually if you follow the way that I ask question, it's kind of a guide to solve the question. Of course, not all the time, but there is a reason why we like to split them up. Okay, so you look at B. Now, you are asked to determine the quality of the refrigerant entering the evaporator. Meaning, you are asked to find X4. Right, that is the quality of the refrigerant entering the evaporator. And then subsequently pressure of the refrigerant entering the expansion valve. So yeah, so this question is slightly more complicated compared to the way I asked the previous one, but it's not unsolvable. Okay, so for X4, you should be able to find X4. How? I also miss out one information here. Another information that's given to you is that it is removing heat from the space by 900 watts. So meaning QL is 900 watt. So miss out one more information. Now we have enough information. So we are looking for X4, and very obviously, based on all the information that are given to you, you have to start from state 1, because that's the kind of the only place where you have everything. So here, you can find H1, right? From superheated vapor table. So once you found H1, then how do we link H1 to 4? We have this. So this is the one that is given to you. So we know that QL is equals to m dot H1 minus H4. But QL is in watts, so again, take note of the units. Now you can move things around, you can get H4. So once you get H4, We know that at state 4, we know that P4 is, let's write here. We know that P4 is equal to P1. Right, same pressure level. We always assume that there's no pressure drop, so they are at the same pressure level. P4 is P1, which means H4 is equal to just HF at 100 kilopascal plus X4 HFG at 100 kilopascal. So from here, then you can get X4, and X4 value should be about this. Okay, so far? So now we have obtained X4. Then we go back to the question. Pressure of the refrigerant entering the expansion valve. So meaning we are looking for P2 or P3. Right? So how do we link what we have here to 3? This is something that you must know. So now we have everything at state 1. We have everything at state 4. So everything that we have here are all at the bottom. Right? So now we want to link this to the top. How? There is a very straightforward way. Like really straightforward. You learn this in class. It's something that you must know actually when you are dealing with this cycle. You did this in your lab also. Even though some of your lab did it wrongly. Oh yeah, I haven't written. I'll return it soon. This one. This is a rules that will not change whether you are dealing with ideal or actual. For our analysis at least. Of course, you know that in actual it will change a bit. But for analysis, H3 is always equal to H4. And we know that H3 is as saturated. So let's say we put state 3 here. Easier. And we know that this is saturated vapor. Sorry, liquid. Based on the question. It says that this is saturated liquid. So from here, you can refer to table A12. You will get P3. And this value, I designed it very nicely. It should be very near 1 megapascal. So you can just assume that it is approximately 1 megapascal. So now you have your high pressure, right? The upper pressure. So we can move on to C. So C, determine the power input of the compressor and subsequently the COP of the refrigeration system if the compressor has an isentropic efficiency of 85%. Yeah, actually answer also given that. If you are unable to solve part B, assume the pressure of the refrigerant entering the expansion valve is 1 megapascal. So if you cannot solve A, then just jump straight to, cannot solve B, then you can jump straight to C. So you are given P2 and P3 equals to 1 megapascal as well. Okay, so now you need to find out what is the power input of the compressor. You are given the efficiency of the compressor as 85%. And you need to find out the COP. So to find the power of the compressor, what you need here is, what do you need? You need to find the power of the compressor, right? So power of compressor, you need H2 minus H1. So you need H2. Right? You need H2. How do we find H2 then? This then is the standard way that you have been learning. So we go back to the beginning. P1 100 kilopascal, T1 negative 10 degrees Celsius. We find S1. So why do we find S1? Because we want to find H2S. So we know that S2S equals to S1. So this you will need to do interpolation. You will get H2 value from interpolation. So once you get this, then we make use of the isentropic efficiency of the compressor. H2S minus H1. So for a compressor, the ideal value or the isentropic value will be lower than the actual value. So the actual value at the bottom, because you want them to work on the same pressure level. So the pressure won't change. Then it means that the actual compressor will need to put in more work in order for the same thing to happen. So then from here you can get the H2 value. And once you get the H2 value, you can sub this back into this equation. Then work-in value should be just about this value. It should be about this. So once you found work-in, then COP of the refrigeration system is just QL or work-in. QL is given by the question. So the value is about this. Okay, so once you are done with C, let's just finish this up. So D is a bit of a more theory question also. But it does involve a bit of calculation. So compare and contrast the COP calculated in part C. So you want to compare the COP that you have just calculated to the COP of the reverse Carnot cycle between the same operating temperature limits. So this is where the negative 4 degrees Celsius and 10 degrees Celsius, was it 10? 27, sorry. The 4 degrees Celsius and the 27 degrees Celsius come into play. So provide an explanation for the difference in COP values and by considering the factors that contribute to the efficiency of each system. So you can give up the later part if you want, but at least do the calculation. So like I showed you just now, in this case, this is just the TH, and this is the TL, and then you have your work in. So the TL is 10 degrees Celsius here, TL is 27 degrees Celsius. Sorry, this is 4. Why do I keep thinking 10? Right, okay, so you need to compare the COP. So again, come back to the question. You need to compare the COP of the reverse Carnot cycle with the COP that you have just calculated. So which means you should at least calculate the COP of the reverse Carnot cycle. And how do you calculate this? We use the temperature equation. And if I'm not mistaken, equation should be also given to you. Let's check. Yeah, so it's here. So this equation. Okay, so questions given to you, you use the equation, you calculate this, you will get 12. Okay, the calculation, this should be in terms of Kelvin again. So if you calculate this, you will get 12. So obviously we know that COP of the reverse Carnot cycle is higher than the actual COP. Right, so what is the reason? Because reverse Carnot cycle assumes reversible processes with no irreversibility, or the with no reversibility can don't write also lah, because it's saying the same thing. While the actual cycle is subjected to various irreversibilities such as friction and losses. Also, not to forget that the actual cycle also included an irreversible process. Okay, my sentence is not complete one, so which is the throttling process. So remember I mentioned the throttling process is, no matter how ideal it is not a reversible process, because it's just throttling. If it is a turbine, then it can be assumed to be reversible. Okay, so these are the answers here, as you can see. Okay, so any questions? This is where I will stop today. Next class I will discuss last year paper. I won't discuss the January paper because usually the short set paper is a bit simply said. So I will discuss all the main set paper. Do you guys still want to class on Thursday? Because if we are following the same speed today,